Hello, I'm Roshan recording experiment 4 Unix lab. This experiment is about base conversion. So here we have 5 base conversions. So I have put them inside a switch case to accommodate them all in a single program. Let's go one by one. The first one is decimal to binary conversion. So in decimal to binary conversion, we first take the decimal value as input, and we have a variable named b. It's an empty variable. Now inside a loop, we are going to do a set of instructions for manipulating the input DEC and to get the output in B. So first, what we do is we have to do this certain number of steps until the DEC, the value that is input, becomes 0. Now the first step is we take the modulus of the number which is input. Uh, like we'll take the modulus operation with 2. So any number a modulus operation with 2 will give a 0 1. So basically we're converting it to a binary number which is going to be stored in B, and now what we do is we divide it by 2. So every time we take a number, we take the modulus operation, so we get a 0 1, then we reduce it by half, then again we repeat the same set of operations again. So each time this loop runs, the value of B increases, and each time when the value of DEC becomes 0, the decimal value, the binary value of the input decimal number will be inside B. Now we echo it. So after that, the next conversion technique is binary to decimal. In binary to decimal conversion technique, first we take the binary number as input, then we have two different variables named DC and P. Now while the input value is not equal to 0, we have to do a certain number of steps. So first one is we take the mode, we don't divide it, we do a modulus operation on the input number with 10. Now a modulus operation with 10 is always affecting the last digit, so it will give you the last digit of any number when you do it, give a modulus operation with 10. So now the last digit is in C. Then what we do is we divide it, that is we eliminate the last digit by dividing it by 10. Now the next task is to see what is the value of that place of that number. So um, every place has their own value in the powers of 2. So the unit place has 2 power 0, the tens place has 2 power 1, the hundreds place has 2 power 2. So it's always on the powers of 2. The first time when this loop runs, uh, it is on the power of 0, so that is 2 power p, and the value of p was initialized 0 here previously. So 2 power 0 will give you a answer 1, so value of d is 1. Now we multiply the number we got, the digit we got, with d. The d is the value we got after doing the power uh, operation. Now we add the d to x. X is the variable which is gonna have the input. Now we increment p, because every time the loop runs, the power changes from 0 1 to till till n, some n value. So in the end you completely convert the binary value that is entered to a decimal number. Now and the decimal number is later displayed. The next technique is to find octet to hexadecimal conversion. So to do octet to hexadecimal conversion, mm, first what we do is we make the octa value to a decimal value, then we make decimal to hexadecimal conversion. So first we take this octa number, so we read that inside bin. So yeah, here bin will have the binary number that is input, sorry, the octal number that is input. Now we have two other variables named dc and p. Now we do the same operation of converting uh, octal to decimal, like we did for binary to decimal. So instead of having the value of places in the powers of 2, here we have in the powers of 8. So with the powers of 8, then we get d, and we multiply the d value with the last digit we got, and then later we keep on adding this number DEC to x, and x will have the output value, the decimal value of the octal number in there. Now we do decimal to hexadecimal conversion, where we simply divide the number. We take a modulus operation with 16. So once you do modulus operation with 16, you'll see if the number which you get, that is after getting modulus operation, the result of that expression is in s. So if the value of s is less than or equal to 9, if it is less than or equal to 9, we have a variable bin, and bin is going to have this s appended to it. And once s is appended to it, we again perform the modulus 16 operation after, as you can see, this in this divide loop we always divide it by 16 and then do the modulus 16 operation again here. So once you divide it by 16, you do the modulus 16 operation. Now you again keep on choosing, if the value is below 9 or equal to 9, that value itself is the hexadecimal equivalent. Otherwise it is going to be, if it's going to be 10, it's going to be A, for 11 it's going to be B, for 12 it's C, and for 13 it's D, 14 it's E, otherwise like for 15 is F. So the if else if ladder helps to identify the actual replacement for the decimal value, and now the value we got is going to be reversed using the pipeline operation and rev command, and the reverse values um, displayed. This is a hexadecimal to octal conversion, that is the fourth one. So this demonstrates how to do them using ibase or obase. So ibase is what you want to, uh, like from where you are the input base value, and obase is the output base value. So input base is in 16, that is hexadecimal, and the output mean it is in uh, octal, that is 8. So once we have the number, we use this function and we convert it to octal, the hexadecimal number to octal number, and we can simply echo it. Now the fifth one is decimal to hexadecimal conversion. We already saw it, so we just do a modulus operation by 16 on the number, and based on the reminder we get, if it's less than or equal to 9, that number is itself is the hexadecimal equivalent. Otherwise, if it's 10, it's A, and so on. uh, yeah, and the result will be in bin, and later we had to reverse it using a pipeline operation and then display it. And that is all. Thank you.